Hey guys, I am going to discuss assignment 2 calculus of variation BSc third semester. In this problem we need to show that the functional I of y of x which vary from 0 to 1 2yx plus y dash dx defined on the space C1 interval 0 to 1 is a collection of all first order continuous differential function which is continuous on the function y naught of x is equal to x in the sense of first order proximity. So before proving this statement, we have to clarify the statement. We have to clarify the concept before proving this given statement. So that is the concept is, so we can say that is a continuity of a functional. So now here we can say that so now here the continuity of the functional we can discuss as, so we can say that a functional I of x defined on the class C, that is a collection of all continuous differentiable function y of x is said to be continuous at y is equal to y naught of x. So for any epsilon there exists a delta such that mod of I y of x negative I y naught of x less than epsilon whenever mod of y of x negative y naught of x less than delta. So this is called as zero order proximity. But if I want to discuss the continuity of the function up to nth order proximity, up to nth order proximity, then for any epsilon greater than equal greater than 0, there exists a delta such that mod of y of x negative y naught of x less than delta, mod of y dash negative y naught dash less than delta, up to we have to go up to the nth order derivative, that's a mod of y to the power of n negative the nth derivative of y naught less than delta. If all the derivative less than delta, then we can say that the difference of mod of the functional I of y of x negative the functional y naught of x less than has to be epsilon. So we can say that the functional is said to be continuous for the nth order proximity. So by using this definition we will prove our given statement. So now here we need to consider, let us consider the functional, though we can say the I of y of x is equal to integration from 0 to 1 2 times of y of x plus y dash of x dx. That is a function, let us suppose that is a 1, it is a given. So now we need to show, that the functional I y of x is continuous on the function y naught of x in sense of first order proximity. So we need to show that for any epsilon greater than 0 there exists a delta greater than 0 such that for first order we need to take mod of y of x negative y net of x less than delta and y dash of x negative y naught dash of x less than delta, and we can implies here the difference of the function y of x negative difference of the functional y naught of x has to be less than epsilon. So by using that we have to simplify this expression, that is a mod of I of y of x negative I of y naught of x. So this is equal to, that is a mod of the integration from 0 to 1, it will give 2 times of y of x plus y dash of x dx negative 0 to 1. Replace the y by y naught, the 2 times of y naught of x plus y derivative of y naught of x dx. So this is equal to the mod of 0 to 1, 2 times of y of x plus y dash of x dx negative 0 to 1, 2 times of y naught of x is given, that is a x, and its derivative will be, that is a 1 dx. So by using the algebraic property of definite integral, that is 0 to 1, that 2 times of, take the 2 as a common, then we will get y of x negative x plus y dash of x negative 1 dx. So now further by using the triangle law of inequality, mod of x plus y is less than equal to mod of x plus mod of y. So by using that we can write here, that is the mod of 2 times of 0 to 1 mod of y of x negative x dx plus the integration from 0 to 1 mod of y dash of x negative 1 dx. Take the mod outside, so here will be the 2 times of mod of y of x negative x 0 to 1 dx plus mod of y dash of x negative 1 into 0 to 1 dx. So here will be 2 times of, that will be delta, and here will be, that is the x 0 to 1, here will be also delta, that is the x vary from 0 to 1, that is 2 times of delta and plus delta, that should be less than equal to 3 times of delta. So further we can say that it implies the mod of the functional I of y of x negative I of y naught of x will be less than equal to 3 times of delta. So now equate, that is epsilon. So now from here value of epsilon is equal to 3 times of delta. So by using that we can find that delta is equal to epsilon by 3. So therefore we can say that the difference of mod of the difference of functional I of y of x negative I of y naught of x, that is less than epsilon for when mod of y of x negative x less than delta, and its derivative, that is y dash of x, and the derivative of x, that is 1, less than has to be delta. So we can say that the functional I of the given function I of y of x is a continuous at y naught of x is equal to x in the sense of first order proximity. Hence the given statement become proved. So this is a very quite final answer. So now here we need to show that the given functional attains strict maxima on the curve y naught of x is equal to 0. So before proving this given statement, we have to clarify the concept. So let us clear the concept. So now we have to clarify the concept extrema of the functional. So then the functional I y of x is said to attain a strict maximum on the given curve, that is y is equal to y naught of x, if and only if we can say delta I has to be less than equal to 0 and delta I is equal to 0 only for y of x equal to y naught of x, where delta I can be written as, that is functional of y1 of x, negative function of y of x, and y1 is a neighborhood of y of x. So the difference is known as variation in the given functional. So this notation denotes, in other words we can say the increment, or we can say that variation. So the variation has to be less than equal to 0, and variation has become 0 only for y of x equal to y naught of x. So now by using so now here let us consider the given function, that is I of y of x is equal to integration from 0 to 1 x square negative y dash to the whole square. So now here should be, that is the y square, not y dash square, there should be y square. So the given function I of y of x equal to 0 to 1 x square negative y square dx. So now take the variation delta I, that is difference of functional of y of x and the given curve y naught of x, that is I of y naught of x. So this will be, that is 0 to 1 x square negative y square dx negative 0 to 1, that is x square negative y naught whole square dx. This value is equal to, that is 0 to 1, that is x square negative y square dx negative 0 to 1 x square, this value that is 0 x square dx. So by using the property of definite integral, if the limit is same, we can take the common 0 to 1, it will give x square negative y square negative x square dx. So from here it will give 0 to 1, this part get cancel out. So now further we can write negative y square dx. as you can see that here the integration in terms of dx. So take y square, y here y will work as a constant. So take negative y square as a common outside the integral and write as 0 to 1 dx. So this value is equal to negative y square, and this integration value will be that is 0 to 1, that is negative y square multiplied to 1. So here we will give the variation delta I is equal to negative y square. So as we know that a square of any real number is always greater than equal to 0. So if we multiply by negative sign, negative y square, it will give always less than equal to 0. So from here we can say that this will be always less than equal to 0. It is possible only when y is non-zero, and delta I is become 0 only for y is equal to 0. So we can say that delta I is less than equal to 0, and delta I become a 0 only for, or we can say that only for y of x is equal to 0, or this value is equal to y naught of x. Hence it satisfies the condition from strict maxima. So we can say that the functional I of y of x attains strict maxima on the curve y naught of x is equal to 0, and this is our required final answer. So now in the problem third, it is very important according to paper point of view. So this theorem is known as, that is we can say, the Euler differential equation. It is also known as Euler differential equation. So now we need to prove that a necessary condition for the functional I y of x vary from x0 to x1 f of x y y dash dx to be a extremum is that it has to be it has to satisfy the condition del f upon del y negative dy dx del f upon del y dash has to be 0 with boundary conditions y of x1 is equal to y naught and y of x1 is equal to y1. So now we have to prove the statement of Euler differential equation. So first of all we need to draw the graph. So now here, so we can write here, let us suppose y is equal to y of x be the curve joining the points, that is a of x naught comma y naught and b of x1 comma y1, and which make the given functional, that is I y of x, the given functional we can say that is I of y of x an extremum. So now further we need to consider, or we need to assume, y is equal to y of x plus alpha times of eta of x, that is a neighboring curve of the given curve y, where eta of x, that is a non-zero quantity, and alpha is a parameter, be a neighboring curve joining these points. So that it will satisfy, so that at the points capital A and capital B, so we can say that at a point A, you can say at a point, this point A, the distance between neighboring curve this and this having a zero distance, neighboring eta of x has to be 0 at a point. So we can say the eta of x naught is equal to 0, and eta at this point, at a point B. So now here eta of x1 has to be 0, and alpha is a parameter that is independent of x, and eta of x is arbitrary continuous differentiable function of x. So that is very important. So now further we need to differentiate the y, this curve, that is differentiate of y with respect to, it will give y dash of x plus alpha times of eta dash of x, and replace y by y plus alpha times of eta of x in functional, in the given functional, then the functional in terms of alpha will be, that is it vary from x0 to x1, that is a capital F of, that is x comma y plus alpha times of eta of x comma y dash plus alpha times of eta dash of x dx, because this functional depends on the parameter alpha. The whole quantity will be depends on the alpha, so this function become the function of alpha. So let us suppose that is the equation number 2, and let us suppose this neighboring curve, that is equation number 1. So now further we need to differentiate I with respect to alpha, then di over d alpha that is x0 to x1, because f is a function of x, y, become a x, y and eta, y dash and eta dash. So we will apply a chain rule, that is del f over del x, and here will be del x over del alpha, del f over del y over del alpha, plus del f over del y dash over del alpha dx. But alpha is independent of x, means alpha does not depend on x. It implies del x over del alpha has to be 0. So by using that, our above derivative, sorry, di over d alpha will be x0 to x1. So this quantity will be 0, equal to 0. So here will be, that is whole quantity will be 0, plus del f over del y multiply to. So now differentiate the y with respect to alpha, neighboring curve, that is y of y plus alpha times of eta. If we differentiate y with respect to alpha, this quantity will be 0 and this will be quantity, this quantity will be 1, so remaining will be eta. So here will be, that is a eta, plus del f over del y dash, and derivative of y dash with respect to alpha will be eta dash from here. So therefore that is d of x. So now we will use here for finding a stationary point, that is the critical point. We need to put di over d alpha has to be 0. If we put di over d alpha 0, whole integration from x0 to x1, that is del f over del y multiplied to eta of x, plus del f over del y dash multiplied to eta dash of x dx is equal to 0. So now here, now open this integral, integration from x0 to x1, del f over del y eta of x, plus integration from x0 to x1, del f over del y dash eta dash of x dx is equal to 0. So now use here, that is integration by parts. As we know that integration of u multiplied to v dx is equal to, take that is a function first and that is a function second. So take the u as the outside first function, take the integration of v dx negative, take the derivative of first function, take the integration of second function, and take the whole integration dx. So this is known as integration by parts. So by using that, so we will take, that is a first function and that is a second function. So now here integration from x0 to x1, del f here will be, that is a dx, del f over del y eta of x dx. So now take the outside del f over del y dash integration of eta dash of x, it will give eta of x. Negative integration from x0 to x1. Take the differentiation of this first function, that is del f over del y dash, or this integration will be, that is eta of x, and a whole integration dx is equal to 0. So now here substitute the lower limit and the upper limit. So here will be integration from x0 x1, that is del f over del y eta of x dx, plus, so upper limit a lower limit, after substitution it becomes 0. Negative integration from x0 to x1, it will give d over dx, that is del f over del y dash dx is equal to 0. So now you can see the eta of dx. So here will be eta of dx. Eta of dx take as a common. So we will write here del f over del y negative d over dx of del f over del y dash, and here will be eta of x dx is equal to 0. So further we can say that by using the property of definite integral, and if the integration from a to b capital F of x dx is equal to 0, and f is a continuous, then is it f of x has to be 0. So by using that we can write here del f over del y negative d over dx del f over del y dash has to be 0, or we can say that eta of x is a arbitrary continuous differentiable function. So in last we can say that this equation must be satisfied by y if y is to make an integral, that is a functional I is extremum, either it can be minimum or maximum. Hence our given is Euler differential equation, that is it is approved, and this is a very quite final answer. So now here we need to prove third Euler equation. So here in the given statement it should be here, that is a y dash. So we need to give the proof, we need to derive the given statement. So now by Euler's equation we know that del f over del y negative d over dx of del f over del y over dash is equal to 0, that is equation number 1. So now del f over del y dash is also a function of x comma y dash. So that is, we can say that del f over del y dash is equal to psi of x comma y dash. So we can give the another name, del f over del y dash is equal to phi of x comma y dash. So now we need to find the derivative of this function. So differentiate the function del f over del y dash. So that is, we need to find the derivative of function psi of x comma y dash. But psi depends on three variable. So we will apply a chain rule, that is del phi over del x and del x over dx plus del phi over del y and here del y over del x plus del phi over del y dash and del y dash over del x. Here will be 1. This quantity will be 1. It will give del phi over del x plus del phi over del y and del y over del x, that is a y dash. Here will be del phi over del y dash and del y dash over dx. Again differentiate the y dash with respect to x, it will be y double dash. So now replace the phi by del f over del y dash, that is d over dx, del over del x of del f over del y dash plus del over del y, that is del f over del y dash and y dash plus del over del y dash, that is del f over del y dash multiply to second derivative. So it will become del square f over del x del y dash plus it become del square f over del y dash multiply to y dash plus del square f over del y dash square and multiply to y double dash. That is equation number 2. So now put, or we can say the substitute the value of d over dx of del f over del y dash in 1, then it will become del f over del y negative del square f over del x del y dash plus y dash del square f over del y dash plus y double dash del square f over del y dash whole square is equal to 0. So by simplifying we will get del f over del y negative del square y over del x del y dash negative y dash del square f over del y dash negative y double dash del square y del square f over del y square is equal to 0. So this is the third form of Euler differential equation, and this is our required final answer. So now here we need to show that if the functional f is depends on only y dash, the extremal are all the straight line. So that is, all a straight line means we need to prove that y is equal to in terms of ax plus b. So now here, so now here the given functional f is a function of only y dash. It implies we can say that f is independent of x and y. If f is independent of x and y, then del f over del x has to be 0 and del f over del y has to be 0. And from here we can say that if I differentiate this function with respect to del y dash, then become del square f over del x del y dash again will be 0. And if we differentiate the second with respect to y dash, it become again 0. So by using Euler's third equation, that is del f over del x negative del square f over del x del y dash negative y dash del square f over del y dash negative y double dash del square f over del y dash square is equal to 0. So this quantity will be 0. Again it will become 0. Again it become a 0 negative y double dash del square f over del y dash is equal to 0. As f dependent on y dash, so this quantity has to be non-zero. So now from here we can write negative y double dash del square f over del y dash is equal to 0. It implies double derivative has to be 0, where second derivative of functional f with respect to y dash is that has to be non-zero. So now on integration on both sides we will get y dash is equal to a as a constant. So on again integration, y of x will be ax plus b, where a and b are, it implies again on integration y of x is equal to ax plus b, where a and b are constants. So therefore it represents the equation of straight line. Hence it is proved, and this is our required final answer.